So there's a lot of cycling in the cell just at that border right between S and G1. Do you understand that? So that's a cycle of proteins. Proteins that cycle during the cell cycle. So let's look at what happens. Here's the origin of replication on double-stranded DNA, right? And this is in early G1. So after anaphase, right, is where those chromosomes pull apart and the nucleus forms around, or the membrane forms around the individual nuclei, the nuclear membrane. And we're in early G1 there. And what happens is this origin of replication, right, is now in a position where it can be, if proteins can bind to it. So this is after anaphase at early G1. And the thing is, you're forming at anaphase, the chromosomes are separated, right? Beginning to form the nucleus around there. But before that membrane is formed, right there in early G1, the cells, proteins in the cytosol can get into that nuclear region and form complexes, okay? So anyway, here's the CDC6P protein. It's a protein that activates replication. So right during this period here, it binds to the origins of replication. Sometime between early and late, so right around sort of like at late G1 phase, there's a complex of proteins that's called the MCM complex that binds to multiple places. It binds close to the origin, it binds further from the origin. There can be this complex recognizes DNA sequences and binds in several places, right? So one of these things, one of the proteins in there is called RLFM, which is the replication licensing factor. Essentially, a cell cannot begin to replicate DNA at the origin unless it has that replication factor there. So during G1, the CD6P protein binds, it recruits or induces the binding of the MCM, and you get to this sort of a structure here, and this is called the closed complex or pre-replication complex. Closed because the DNA is double-stranded still. You know, it's in duplex with each other, the two strands of DNA. And it's a pre-replication, they call it pre-replication complex in your textbook because DNA hasn't replicated yet, well, hasn't started. Everybody still sort of with me? Okay. Sometime right here, you can see during the activation, going from G1 into S. So when we were at that activation period, that's when I told you this cyclin was made, right? This one happens to be cyclin B. And what cyclin B does when it's made, so it accumulates during G1, and in essence, right at this gate here, gateway, it's at its maximum. And it binds to another protein, a protein that's called a CDK, which is a cell division kinase. These kinases, remember, are proteins that put phosphate groups. They phosphorylate other proteins. So cell division kinase is a kinase that's activated. And this particular CDK, this kinase here, is cyclin dependent. It's only active when it's bound to cyclin. That's what this blue thing in that dash means, that those two are in complex. So cyclin B is made right at the gateway there. It accumulates, and there's a lot of it. It binds to this particular CDK, right, cell division kinase, and it activates it. This CDK is called CD7-DBF4. This complex has kinase activity, and it begins to phosphorylate some of these proteins. It phosphorylates CD6P, it phosphorylates MCM, and if it puts enough phosphate groups on them, those proteins no longer have affinity for the origin, for each other, for the DNA, and they come off, right? They come off of that complex, so they come out of the closed complex. Did I say that well enough? This protein here, this cyclin B-CDK, phosphorylates both of those. It also phosphorylates another kinase. It's called the CD7-DBF4, which is another kinase. And so this guy phosphorylates this guy to activate it, and this guy can now also phosphorylate these. So all of this is to activate these kinases right there at a specific time, right at this gateway between activation and G1 and S, right? We're leaving G1 and we're getting into the S, the synthesis phase. And when it does, when these guys are jettisoned like that, that allows for the replication to continue. And you can see now it's open. It's called an open complex. I don't see it labeled there. It's sometimes replication complex, open complex, right? But DNA synthesis is going on at this origin of replication. Does everybody follow me? Did I say that well enough for you? Right, so the origin at a specific time binds to CD6P and MCM, and they form this closed complex. But that's sort of one of the things that this complex does is it has this factor that says you can replicate when it's time to replicate. One of the things that has to happen once this forms this complex, right, is that these two kinases are activated right at the right time. They phosphorylate those come off, and the origin begins to replicate. So now we have this guy. See, we have the DNA is replicated, so we have the two daughter strands. This whole replicon of the DNA is replicated. There is an origin on both of those, right? We're still in the S phase, but these can't be allowed to replicate again. Why don't they replicate again? Well, there's two reasons. One is that as soon as this guy becomes unbound, right, the CDC6P, as soon as it comes off of this complex there, it's turned over. Even if it doesn't when it's made, when it peaks like this, even if it's not in complex, there are proteins turning over. It's labeled with ubiquitin, it's ubiquitinated, and then turned over in a proteasome. We'll talk about that later. But it's turned over by a proteolytic region in the cell, in the cytosol cell. So this guy's turned over very rapidly. So there's none of this left to start this all over again. There's none of it left to bind to this again. This binding event, right, has to happen way up here, right here, during this thing. During this, they call the window of opportunity. The opportunity where the cell has to bind CD6P and MCM. Called the window of opportunity. That makes sense? Particularly this part here. Turned over, going away. The other thing is the MCM, where does it say that? It can't replicate until the next cycle because this replication licensing factor, right, which is part of MCM, is cytosolic. So remember here this is that anaphase, we're getting into G1, and the nucleus membrane is forming around the nucleus. So now this stuff's happening in the nucleus. This stuff here, right, is turned over very quickly in the nucleus, and no new stuff can get in. So the MCM, the RLFM that's in MCM is out in the cytosol until the next round of the cycle where the cell is ready to get into S at the G1S border and the nuclear membrane breaks down. Then this can get in, form the complex, and interact with that. So that's why they say there's only this window of opportunity when the nuclear membrane goes away that all of these proteins can bind to the origin. The membrane forms around the nucleus so that after replication that occurs on that DNA inside the nucleus, the proteins no longer have access and they can't rebind to the origin and start replication. Can anybody ask a question? Yeah.
So cyclin B, CDK, phosphorylates CDC7DBF4.
Yes.
And then they should do the same thing?
Yes, both of these phosphorylate these proteins here. When this guy gets phosphorylated, it just sort of makes the process go even more. The process is to ensure that this happens very quickly and these fall off and replication can begin.
The pictures RLFM supposed to be with the MCM?
Say this again? Yes. This factor, right, RLF, this MCM is a complex. I think that stands for mitotic complex or something like that. But anyway, this RLF is part of that complex. That's a bunch of proteins. It's not one protein. It's sort of a complex of proteins that are involved. Okay, so that's origin of replication in eukaryotic cells. Now, once DNA synthesis goes on in eukaryotic cells, the problem, because these chromosomes are linear rather than circular, right, like bacterial cells, the problem arises during the priming process. Remember, these Okazaki fragments are 1,000 or so nucleotides long. So we have this is the template for lagging sand synthesis, which has to go 5' to 3'. I numbered that wrong. The template should say, because these fragments have to be synthesized 5' to 3', right? The RNA is on the primer. So this template should say 5' to 3'. I just labeled that wrong. So change that. Does that make sense? Mm-hmm. So you put on a primer, right? The strands have to come apart. You put on the primer and you synthesize in this backwards direction on that template. This is where the replication fork is. And the other strand of the DNA is the template for leading strand synthesis. So as the two parent strands come apart, the leading strand goes this way, lagging strand has to wait for primer and they go backwards. You all with me? Yes.
Is it labeled correctly?
It is labeled correctly?
Yeah.
5'. Well,
because the arrows are pointing 5' to 3'.
Yes, no, but what happened, this template strand is what I labeled. So this should be the 3' strand end of the template, and the 5' end of the template, because this is the 3' end that was made in the 5' end. The prime is on the 5' end. Isn't that right? Am I confused or not? So here's your template, right? And if the template is let's just put it up there, 5' and 3', right? The other guy has to be anti-parallel. So that synthesis has to go here like this and go that way. This opposite strand has to be 5' to 3'. And the strand that's being synthesized also always the direction it's going in. This is the 3' hydroxyl. So that's the 3' end. The RNA primer is always starts at the 5' end and then goes this way. So that's leveled up, right? So the template strand always has to be anti-parallel. So that should say 5' to 3' on the top, labeling the template. But you're right as far as labeling new strand that's being made. The red is 5, and that's the 3' end. The arrow is indicating the direction of synthesis. Always goes towards the 3' end. Synthesis is always 5' to 3'. Yes? Look at it, and if you have to, we talk about it, we can. Okay, so here's the problem. This is the end of a chromosome, right? One of the templates. And all of a sudden, you don't have 1,000 nucleotides here. So there's no place for that primer. You have to separate the strands by 1,000 nucleotides before you can prime, right? This guy would have to prime outside of that region. So what that means is that these nucleotides here, however many they are, cannot be replicated because you can't prime, so you can't make the DNA strand. Well, it turned out if you look at the ends of chromosomes, they have what we call telomeric DNA. And telomeric DNA is a repeat sequence. It's usually 6 nucleotides. It can be between 6 and 8. It's 6 in humans, right? Such as TTAGGG. And it's repeated on the end of chromosomes. In fact, it's repeated so many times that if you take all of those repeats in humans, it's about 5,000 nucleotides long. Do I have that there? 5,000 base pairs in humans. So at the end of the chromosomes, there's 5,000 base pairs that have that thing repeated over and over and over again. In mice, it's even longer. In mice, it can be up to 60,000. So it can be up to 60,000 total base pairs with the same repeat, 6 letters over and over and over again. Everybody understand that? Several reasons for that. One is that those telomeric regions bind to a protein. And when this protein binds to these telomeric proteins, it prevents the ends of chromosomes from sticking together. If you have 2 pieces of double-stranded DNA and they're just naked, no protein, they'll stick together. They'll go together like glue, right? And that's a real problem. So when you put this protein on these repeats, they don't stick. It keeps the chromosomes from sticking together. The second thing is it serves, essentially, it is a template, but you need another enzyme to take care of that. And the enzyme is called telomerase. Telomerase or telomerase. Telomerase is a ribonucleoprotein particle. What's a ribonucleoprotein particle? What does that mean? What's ribonucleo? RNA protein particle. So it has RNA and protein. So this is a molecule or a particle or whatever. It's a complex of RNA and proteins that has an enzymatic activity. So telomerase is a ribonucleoprotein particle. Okay? RNA in there. This is about 400 to 500 nucleotides or base pairs. Nucleotides. It depends on nucleotides, not base pairs. 400 to 500 nucleotides depends on the species. In humans, it's about 450, right? And within that RNA, that's part of this telomerase molecule, there are several copies of the 6 nucleotide repeat. So it's the same, it's the complement of that 6 nucleotide repeat. So if this is RNA, right, the RNA would say it would say AAUCCC. AAUCCC in the RNA. Does that make sense? It will when you show the picture. So here's what happens on the end of